All right, welcome to the last day of the summer school. We're here for our second talk of Professor Collin Broholm, Magnetism and Superconductivity in Weyl and Dirac semimetals. We'll go ahead and get it started.
Well, thank you very much and good morning. And I'd like to express my appreciation to the organizers for inviting me for this meeting. It's been really a joy to meet many of you, and I hope to stay in touch. And I certainly would invite people who'd like to do work with neutron scattering, to contact me, or people who are interested in how to analyze scattering data. You know where I am, hopefully at Johns Hopkins University, and I'd be happy to communicate with you about such things. Now, yesterday I got through about 2/3 of my talk, which I think is fine. Are you going to provide the slides for the?
Yeah, in the lectures.
In the lectures. So you can check out, the rest of it that didn't come through, but I think it's fine. And I'd rather just go to the new topic. And if I unexpectedly have extra time, I could go back and talk a bit about what I was going to say about pyroflow, classical and quantum magnetism. Also very interesting, I think. But in this lecture, I'd like to turn now to metallic systems and their magnetism in particular. And it's actually a much more complicated topic, and we can't expect the same level of kind of specificity and accuracy when we interact between experiments and theory. And it's also much more interesting for that reason. There's really much more variety in the behaviors that we can see. So it's an interesting but quite different area. And the point that I'd like to take here, so you've heard a lot about topologically protected aspects of electronic band structure and Baryk curvature, quantum transport properties. This is actually a little bit outside of my kind of normal area of expertise. It's quite normal that I would actually take a slightly different point of view. I'm interested in what are the effects of these electronic band structures on the magnetism. What kind of unusual forms of magnetism or superconductivity actually could come out of having those topological features in the electronic band structure. I'm also interested in how the magnetic order can influence the topology of the electronic band structure. And we're interested in how by changing the magnetic order, we might be able to change the quantum transport properties. For example, be able to switch the Hall response by applying magnetic fields. Those kinds of things we're quite interested in. So some of this work has to do with exploring ordered magnetic structures, and some of them are actually quite complicated. These are not collinear antiferromagnetic structures, but some kind of spiral structures tend to come out of these things, and those can be quite interesting and complicated to fully determine, and so I'll tell you something about that. We're also going to want to think about how the interactions actually take place. So I have my spins. They'll in many cases be either rare earth or transition metal spins, and then they're somehow interacting with each other by an exchange interaction. And so we're interested in what are the special aspects of this exchange interaction that result from the unusual electronic band structure. Okay, and so we're going to work both with rare earth and transition metal magnetism. And at the end, so the last third of my talk is about superconductivity. And I'm going to talk about mu and spin relaxation in that part of it. And we'll see if it's not certain that I'll be able to get to it, but we'll see how it goes. All right, so these are the kind of three topics that I thought I'd talk about. So it's a rare earth material which is structurally is non-centrosymmetric, and so this band structure actually enforces Weyl points in the electronic band structure before it undergoes magnetic ordering at all. And so we were interested in how are the interactions unusual or different because of having these Weyl points in the electronic band structure. And they actually give rise to some quite interesting helical spin structures that we'll be looking at, and we'll also be looking at the magnetic excitations and extracting from that a quite detailed picture of the magnetic exchange interactions. Then we're going to talk about manganese-3 tin, which is part of a family of manganese-3X materials that has received a lot of attention since about 2011. And that's because it is actually a Dirac semi-metal, but then undergoes a phase transition to an antiferromagnetic order, which has the symmetry of a ferromagnet. So it has a spin-split electronic band structure and actually has an anomalous Hall effect in the presence of almost no magnetization. There is actually magnetization, but it's extremely small magnetization. And this material is really quite interesting, both from a fundamental standpoint and also because some applications are coming into view, and I'll say a little bit about experiments that we're doing to explore more the application potential in this material. And then finally, we're going to talk about the superconductivity in a Dirac metal, lanthanum, copper antimony. This has no magnetism yet, but there is the possibility of putting a rare earth element in that has magnetic moment, and we're also working on that. We'll talk about it. Just like in the previous lecture, I'm going to add in some aspects that I think to explain a little bit the techniques that we're using. And for this material, there's a little bit about the spectroscopy that we use and how we work with these kinds of materials. Actually, the analysis that was undertaken by Chris Lugaros, who I'll say a bit more about later, that was quite advanced for us, and I'll say a bit more about how that was done. And for this material, I'm going to talk about how we use both polarized neutron diffraction and X-ray, magnetic X-ray scattering to determine the magnetic structure and analyze the very complex magnetism of this system. In this case, if I get time for it, I'll talk about muon spin rotation or muon spin relaxation that we use to determine the internal field distribution in the superconducting state. The interesting thing about this material is that it actually has type 1 superconductivity for one field direction along the uniaxial direction, and it has type 2 superconductivity in the other direction. So this is kind of an unusual aspect of this. And all of these things are published, either actually published or in archive articles. Actually, this one I think is now. This one has appeared in print, but it's also available in archive. Okay, so the first part is going to be about neodymium aluminum silicon, and these are the collaborators. All of these are quite big projects, that involve people doing synthesis. In this case, that was done in Faisal Tafti's group, and people doing density functional theory. That was David Vanderbilt, and also this group, Staunton and Juba, working with there. We worked with Predrag Nikolic, who does sort of analytical field theory analysis of these kinds of things. But I wanted to highlight two individuals who were my postdoc at the time, Jonathan Gaudet, who actually brought this project to the group from his sort of internship at Boston College with Faisal Tafti, and we've had a lot of fun, and it's been really interesting to work on it. And then he got Chris Lugaros involved, who's a grad student in my group. He's going to defend his thesis, let's see, next, the week after next, so in 10 days. And then he's coming here actually as a postdoc in Lee C's group. So he's very excited about that. Actually, I hope for those of you who are at Princeton that you'll treat him well. He's a really great guy. I think you'll be able to do good things with him. And yeah, so let me now begin to talk about neodymium aluminum silicon. So this is the structure. It's a non-symorphic structure which has a fourfold axis, but it's a screw axis. And so the neodymium sits on this tetrahedral structure in quite an interesting way. So there's no point of inversion in the structure at all. And so it has actually, I should remember the number, I think it's 56 Weyl points in the electronic band structure before the magnetism starts at all. And this was something that Vanderbilt and his group analyzed very carefully. And What was interesting in a sense for us, though I have to say that we sort of, the material came along because of its interesting sort of magnetic properties. We decided to look at it, but now a little bit in hindsight, we recognize that it's a really good system to try to understand the nature of, we could say, RKKY interaction resulting from an electronic band structure that has Weyl points. And so how are those different? This can be an emphasis because the 4f electrons in this material are not at all involved with the transport properties. They're really very far from the chemical potential. And so we can really think of it in the normal RKKY mechanism where the F electron is causing some kind of a Friedel oscillation in the spin density, which is then impacting another 4f electron at a distant site. And so we should expect some kind of oscillatory nature of the exchange interactions that we should be able to detect in this material. All right, so let me show a couple of the thermodynamic properties. That's the specific heat, just the magnetic part of the specific heat. And you can see this kind of broad hump. Notice it's a logarithmic scale. So this broad hump in the sort of 20, 30 Kelvin range, that actually has to do with the Schottky, that is essentially a Schottky anomaly associated with the other four doublets in this in this Kramer's spin. This is 2s plus 1 is 10, so it's 9. So it's 9 half spin. Oh my God, that's a lot of spin. So there's a lot of levels in the system. So 5 doublets are present, and many of them lie in this energy range. And then finally, you end up with a doublet ground state, and so that determines the underlying magnetism. And then there are actually 2 phase transitions. First, a transition into an incommensurate state, and then at a lower temperature, a transition to a commensurate state. And that's a very, very normal scenario actually for rare earth metals like this. It doesn't have to be a Weyl material for that to happen, but there are some aspects of the incommensurate structure that we think can be associated with the Weyl structure in the electronic band structure. The reason that it tends to happen like this is because the RKKY interaction is a long-range interaction, so it produces typically, I mean, you could say that the spin density in the system likes to oscillate with a certain wavelength, which is associated with nesting conditions on the Fermi surface. And as you throw in the F electrons, they sort of enforce that and eventually end up having this kind of modulation in real space. And so it's quite normal to get this structure. It's also quite normal to eventually get a transition to the commensurate state, and that's because the incommensurate structure cannot produce like a full magnetization of the spins. If I'm having this kind of periodicity which is not commensurate with the lattice, I can't get every spin to be fully magnetized. And that's energetically very unfavorable at low temperatures. And so there's almost always this kind of transition into some people call it a squared up structure. You get some kind of square wave formation, which then becomes commensurate. In this case, it's not it is a commensurate structure, but it is a bigger unit cell than the chemical unit cell. And so this is what happens, and not particularly unexpected. Let's see, then in the susceptibility, we see that there's quite large anisotropy that develops as we cool below the temperature of this Schottky anomaly. And that's as we expect as well, because as we depopulate the excited crystal field levels, then we bring out the intrinsic anisotropy associated with the Kramer's doublet ground state. And so that begins to increase the ratio between the A and C susceptibility as we come to low temperatures. So this is an easy axis system. The spins really like to be along the uniaxial C direction. We also notice that the system eventually develops in the commensurate phase a little ferrimagnetic component to the moment as well. The susceptibility kind of gets flat because we have, it's really a finite magnetization that develops in this field. And that, we'll see why that has to happen. That doesn't always have to happen, but it does in this case. There are little anomalies in the resistivity, longitudinal resistivity, as you go through these transitions, and that indicates some kind of a rearrangement of the Fermi surface resulting from the exchange field from the ordered spin structure. Okay, so then we turn to the Newton diffraction to understand what kind of order is happening. That's always a bit of an exercise and a kind of a, you really don't know when you start these experiments where we're going to find the Bragg peak. And in some cases it can be quite a search for a needle in a haystack, but eventually you do find it, and it's quite nice when that happens. So what's shown here is this actually tells a lot of the story at 8 Kelvin, which is above the phase transition. There's no peak in this range of wave vector. This is along the HHO direction, so it's an in-plane, in the triangle plane wave vector. But then when we cool down to 4.1 Kelvin, there is a little peak that develops. That peak is not at a rational fraction of the wave vector is not a rational fraction, which means that it looks like an incommensurate structure, or maybe a very, very high order rational fraction, possibly. And then as you cool down, there's a slight shift in this peak, and then it also gets a little bit stronger. And then finally, when we cool to lower temperatures, we get to the commensurate state. This is this light blue peak, which sits right at the 2/3 position. So now it's being forced into this commensurate position in order to get a fully polarized rare earth site. And I think, one thing I just want to show here is that the wave vector kind of slides with temperature, and that's also a fairly normal thing. As the exchange field grows, there's a modification of the electronic band structure that changes the interaction, and then you have this kind of thing taking place. There are also some higher order harmonics that are seen. And that means that it's not just a sinusoidal spin density, but there's some kind of edges to it. And those tend to get stronger as you cool down, and it gets more kind of saturated, more square wave-like. And then eventually you get into this commensurate state. And actually what happens is that these higher harmonics actually at low temperatures, they go away, and then they become the ferromagnetic part of the Bragg peak. So this ferromagnetic moment is what it becomes, in a sense, associated with the higher order harmonic, which then goes away. So this is roughly what the spin structure looks like. So the spins are mostly along the c-axis, because that's what the crystal field, Kramer's doublet ground state, specifies, if you will. And it basically has, there's 2 spins up and 1 spin down, and there's therefore a net magnetization that's kind of that's present. I should say that I'm going to slightly update this structure. This is a somewhat simplified version of it, because all of these spins have a little bit of a canting associated with them. They're rocking a little bit back and forth, and that rocking is very, very clear experimentally. We have no doubt that it exists. And that is actually a very important part of the magnetic structure that we do associate with the Weyl nature of the underlying band structure, because that has to do with the presence of a Jarzynski-Maria interaction, which is driven by the lack of inversion symmetry, and comes in as a result of the Weyl physics. So now I'll say a few words about the electronic transport properties. And so the idea is that we will use transport, in this case Subnikov-de Haas oscillations, to learn about the underlying Fermi surface. And the general kind of scheme that's going on is that we would like to understand how the Fermi surface has impacted the particular periodicity that we have of this incommensurate magnetic structure. And so obviously you can do that with band structure calculations, but it's usually difficult to really fix the chemical potential, which can have very big impact on the nesting conditions. And so we're doing the transport properties to pick out the, in a sense, to determine what the chemical potential is in the electronic band structure, and then we can make the comparison between the wave vector observed in magnetic Newton diffraction and the nesting conditions from the band structure calculation. So there are Subnikov-de Haas oscillations, and from those we can extract the area of the extremal orbits, and from that we can extract a characteristic linear dimension of the orbit. So I take a square root of the area, I get some kind of characteristic linear dimension, and then I can follow the temperature dependence of that linear dimension of a particular orbit on the Fermi surface, and we find that that temperature dependence has a similar sort of slope. So dq dt is similar to what we observe in terms of the slope of the in terms of the temperature dependence of the antiferromagnetic wave vector. So what we measure in diffraction is these blue points, and what we see in from Subnikov to Haas is that the linear dimensions of the Fermi surface are changing with a slope, let's say dq dt, which is kind of similar to the magnetic wave vector. So this is a fairly kind of mild connection that we're making between these two, but at least they're not like orders of magnitude off. And so what I'm saying is that we can from this take a hypothesis that this change in the wave vector with temperature of the magnetic structure is actually driven by modifications in the nesting conditions on the Fermi surface. That's what we draw from that. Okay, so now we want to make connection to the band structure calculation, and so shown here is the Fermi surface calculated by Vanderbilt and his group, and then I've overlaid on that two wave vectors that actually are very close to the measured wave vector for the magnetic order that we observe, and we define specifically a minimum and a maximum wave vector, and they end up bracketing the actually observed wave vector for the magnetic order. They have the same directionality as the observed wave vector, and the observed wave vector lies in between these two, as I'll show in a bit. Now, underneath these Fermi surfaces lie all the Weyl points. So the Weyl points are actually quite close to the chemical potential. So these are quite small pockets. The electron density is quite low, but very strongly impacted by the presence of these Weyl points. And so therein lies the assertion that the RKKY interactions are actually mediated by, we could call Weyl fermions, because they are fermions that are very close in momentum space to a Weyl point. And then to make more strongly the connection between the calculated band structure and the magnetism, then I have this plot here, which shows as a function of the as a function of the chemical potential, which is, as I said, not well determined in DFT, then these two wave vectors that I had shown on this chart here, the minimum and the maximum wave vector, that's these two wave vectors. And the observed experimental wave vector is this dashed line here. And then at the point where that one sort of splits the difference between those two nesting wave vectors, that's how we determine what the chemical potential actually is in the system. So we think that that we have a case that the magnetic order and its periodicity is driven by the particular nature of the Fermi surface in the system, but then so then there was so we published a paper that has many of these things and others that I'll have later in the talk, and there was a kind of a response paper that came to that, which was this, from this group, and they said, listen, we've calculated the by using LDA plus U, we calculate the exchange interactions in the system, simply by finding ground state energies for different spin structures. And we are able to stabilize, or what we find is that the exchange interactions do tend to stabilize this particular structure that you observe with that particular periodicity, but we can make it stabilize that structure even in the absence of Weyl points. So they specifically introduced, by modifying the crystal structure, they introduced what's called mirror planes, which eliminated the Weyl points, and yet they still had the same kind of wave vector coming out from it. And so it was an interesting result. And so we dug a little bit deeper into the nature of the underlying structure to understand what how we could make proper connections to the Weyl nature of the electronic band structure. And so, I want to say that this spin structure in the incommensurate phase actually has several different components that are kind of superimposed on each other. So this is the commensurate antiferromagnetic peak, which indicates the presence of a ferromagnetic component. But then we also have this. Sorry, this is in the commensurate phase. And so we have two types of commensurate antiferromagnetic Bragg peaks. There's the 2/3, 2/3, and 1/3, 1/3 Bragg peaks, and they actually correspond to two different polarized components. One component which is polarized along the c-axis, and the other component which is polarized in the perpendicular direction. And so these are those two components. The 2/3, 2/3 looks like this, and that's the transverse component, which we also see. It's very, very clearly observed. Let's see. This is all of these. Let me see. This is all of these points. All of these 2/3. Sorry, all of these 1/3, 1/3 points. All of these points here are associated with this part of the structure. So all of these get superimposed. We see it in momentum space, by the Bragg peaks. These are the three components. They get superimposed, and you get this kind of structure, which is, predominantly what I've shown previously with the C-oriented spins. But the spins are kind of rocking back and forth, have this transverse component. That transverse component is driven by a DM interaction. And it's the component of the DM interaction which is perpendicular to the c-axis that's significant, because that's wanting the spins to actually develop an angle with respect to each other in the plane perpendicular to the d vector. So it gets to be quite a complicated structure, but we certainly do see that structure. Okay, so then we thought we'd take another step and try to actually determine the full nature of the magnetic interactions. Not only observe the wave vector, but really see how strong are the interactions, what's their range, to really make contact with the theoretical work. And so that brought us to inelastic neutron scattering experiments. So actually using the exact same instrument that I talked about yesterday when we were working with this super solid phase, it's a very high resolution spectrometer called CNCS at SNS. I just wanted to show a couple of just pictures of some of the practical stuff, which is what we kind of actually do, if you will, and really getting this right is how you can, draw some physics out of it. And so this was again a situation where you cannot grow big crystals of high quality of this material. We have tried. Our colleague Said Copier has tried, but it seems that the flux growth is really the best way to get at the crystals. But those are very small, so you assemble many of those together, and this is how that's done. You align it with the Lauer spectroscopy. You mount it on the cryostat, and then there's another little trick. Just this, but the ones of you who are experimentalists, these are again very important aspects of making things work. And so here are the crystals. Here is cadmium, which is a neutron-absorbing material in its normal natural isotope. And so that one really blocks out the mounting rod. But then above that, we had a little region where we thought we would reproduce all of the extraneous material that we have because of mounting the crystals, including the glue and all this crazy stuff that we want to actually subtract out. So this was kind of a background sample, and it's very important that we have it in the same cryostat, because this is all dilution-rich instrument, stuff, and so it's a very slow process of cooling and mounting, etc. So in this way, we could actually do our experiment with the crystal, and then just lower the entire thing down to get this thing into the beam, and do that exact same measurement, then do a subtraction, and that was key to making it work. Without it, it just wouldn't work. So these are just little kind of tricks. This is the machine, that's the person, so these are really room-sized instruments, completely covered with detectors 36 meters from the source. And that's the resolution. There are several different configurations, but we can get all the way down to 20 microelectron volt resolution by choosing the incident energy and also some configuration of choppers that are part of the instrument. And so then this is then what you see experimentally. And this is basically crystal field excitations, which we also talked about yesterday. And it's neodymium again, which was actually what we showed yesterday. So it's a lot of stuff that is very similar, but then some things that are different. And so this is what the excitations look like in the temperature above the commensurate phase transition. So first in the paramagnetic phase, this is with red, and so there's a kind of fairly broad peak, and then the second peak, these are kind of the main things which we would think of as the crystal field excitations. And first of all, you see that they lie in the energy range that corresponds to the Schottky anomaly in the specific heat. So that's as we expected. And that's how we knew to use that instrument. You know, we knew that would be the range. And then as you cool down, there's some kind of shifts that take place, but nothing very dramatic. But then when we go into the commensurate state, then actually we get quite a few additional little peaks showing up. And this whole kind of spectrum that seems to be present here, this kind of distributed stuff, actually becomes weaker, and then intensity kind of collects into specific peaks. And then what's happening there is really quite interesting. It's laid out here a bit more. So this is the paramagnetic state, and that's the main peak, and then this is the weaker peak here. And then you get into the incommensurate state, and it's still kind of fuzzy. And then finally, when you come to low temperature, then it breaks out in kind of sharp levels. And what's happening there is that I guess I've got one more thing. Sorry, since I got started. What's basically happening is that in the incommensurate state, there's not a registry of the modulation of the exchange field with the crystal structure. And so each neodymium atom is in its own environment, essentially. It's phase shifts in some funny way with respect to the exchange field. And so therefore, I'm going to find just a distribution of different crystal field splittings. These are all Kramer's goblets, so they all get split as we come along, but each side is having a different exchange field. And so I actually get a very smeared behavior. But once I get into the commensurate state, then there are just two different sites, actually, that are distinguishable from each other, and they'll have their specific exchange field. And that will produce this fairly complicated pattern of multiple peaks, because there's a minority and a majority site. There's an up and two down sides, and they have different amount of splitting observed, and there's a different number of those, and so it gets to be fairly complicated, but in a predictable way. And we're going to fully analyze that whole situation. All right, so this is actually the lower energy part of it, and it's even more stark there. So this is in the incommensurate state. I have this kind of broad peak. I have some intensity over here because I'm at 5 Kelvin, and detailed balance allows you to have some inelastic scattering over in the neutron energy gain side. When you go to low temperatures, that definitely does go away. But this other stuff didn't have to go away. But because it goes away, I know that this actually was a reflection of the incommensurate nature of the system. So in a sense, this is a way of very accurately knowing that you have an incommensurate structure, because I have this whole continuum of exchange fields that have split the doublets. But then when I go into the commensurate structure, I just get two specific energies coming out. So now I have just two specific sides. It's really quite nice. And so this is the picture that happens in the incommensurate state. Many different continuum of different experiences are found. But in the commensurate state, then I have one upspin, two downspins, and those have different experiences. The upspin has always two antiparallel spins surrounding it. The downspins always have both an upspin and a downspin surrounding it. So they have different fields, and this will be the exchange field associated with this side. That's the exchange field associated with the majority spin side. And those get related to the Z component of the exchange interaction in this particular way. And I have to define which, the numbering, etc. But we have, a long-range interaction, so we have to keep track of a whole set of different exchange constants. Okay, so then we have to actually, in order to determine the exchange interactions, we need to also know the crystal field Hamiltonian, and that has to all sort of be simultaneously in a consistent manner analyzed. And this was done in a really quite elegantly by Chris Ligoros. And it was a fairly large calculational activity. What I'm showing you here just cuts through as a function of energy at specific wave vector transfers, but we have the whole wave vector space accessible to us. And so all of the wave vector dependence has to be analyzed, and that will reveal the nature of the exchange interactions. So this is the crystal field Hamiltonian, which can be written in terms of these Stevens operators and tetral harmonics. These are the what's it called, expansion coefficients for the crystal electric field, and those we can extract from all of this analysis. And this is kind of the result of the experiment, which is the dark blue, and this is all of these constants as we got them from our experiment. And then we're comparing it to a point charge calculation, where you just assume the point charges are just sitting where we know that the atoms sit. That is not terrible. I mean, it does get some aspects of it correct, but it's not so good, at higher multipolar regions. We've also compared to a DFT determined charge distribution. So this group, the same group that was involved with doing the DFT to determine the interactions, they also did this calculation of the crystal field effects, and that's also fairly good. But actually, I was a little surprised it wasn't better than that. But it seems that it's quite difficult to get these higher harmonics to come out to the right values. But we're quite sensitive to those in the spectroscopy. Anyway, so that's the analysis of the crystal field excitations. But now these excitations, which are now all measured in the commensurate state, those have been split as a result of the Z component. But then, because of the transverse component, this JXY, there's also some dispersion present. So this is very much like the Ising system we looked at yesterday. There's a little bit of dispersion that comes on top. And actually, if you think of it, then that dispersion, let me say, the fact that these interactions are so anisotropic is actually quite connected to the underlying Weyl structure of the system. The lack of invergent symmetry would tend to accentuate the anisotropy of the interactions. And what we're seeing here, namely that the bandwidth of this excitation here is much less than the splitting between them. That is directly showing experimentally that JXY divided by JZ is quite a small number. We have fairly weak transverse interactions. It really is a very exchange anisotropic system, and we think that's also connectable to the Weyl aspect of the band structure. This is another way of showing the same data, actually, which is just a slice through these same data at 3 millielectron volts, and you can see these things sort of coming into view and leaving view at different energies. So this is 3, 3.5, 4, and 5, sort of moving in this region, get these interesting structures. So there's quite a lot of information in the data, and all of that we're going to try to use to determine the exchange constants. And so that requires this random phase approximation calculation that will include both the crystal field Hamiltonian, the exchange field, as well as so all of this is the exchange interactions. Sorry, this term is the exchange interactions, and that's the mean field component. And we'll both have the Z part, which does the overall splitting, and then the transverse part that does the dispersion. And this is all treated using Green's function analysis in random phase decoupling. And we end up with this expression for the full dynamic correlation function. So it sort of comes back to what I was saying in the very beginning of the lecture, is that we're able to directly calculate the scattering cross section and make comparison to the data. Now, in the case of these metallic systems, we have to, well, in general, actually, we should say, but there has to be some approximation, which is the RPA decoupling. So it's not exact in that sense, but it may be accurate enough to get a good estimate of the exchange constants coming out from that. So then this is now back to the experimental data, and what Chris basically did was that he did a pixel-to-pixel comparison between the calculated dynamic correlation function and the measured dynamic correlation function, and then really wandered through phase space for these many parameters to try to reproduce the entirety of this data set. And that required using a cluster computer, because there are really tens of thousands of pixels that are being, you have to do this fairly complicated calculation along with that. So we had never tried something like that before, and it really was only possible because of the power of the instrument and because of the computational advances. We would never have been able to do it on computational capacity from, let's say, 10 years ago or 15 years ago. It was a pretty high level thing, and then you end up with this type of agreement. So that's the experiment. This is the RPA calculation, and many of the features are quite well reproduced. Of course, there are correlations between these parameters. There are a lot of parameters. There's also a lot of data. And so what Chris did was that he really spanned this very high dimensional parameter space to try to understand by what accuracy we had determined each of the parameters. And so this is each of the many parameters, and then the criterion for goodness of fit as a function of that parameter. And so this again was something you can do with a multi-core processing system, and you can also get the correlation between these parameters. But that is really necessary to make sure that you're not really fooling yourself. And so the error bars that I'll now show are we're quite confident about those error bars. Like, we really know when I show this point, this is the range that we have, and for this point, that's the range. For these, we actually know them quite well, and Chris understands what it is that happens when you vary this particular parameter as opposed to varying these parameters. And so this is our experimental result, and each of the points is the Z component of the exchange interaction for each of the interactions that are indicated on this figure. So this is something that you can't look at for a minute and kind of absorb. But the main point I just want to say is that it now is possible to really read off these exchange interactions by this process. The high quality data, the analysis of the full pixelated data set, and you can really get these exchange constants coming out. And then we can make comparison to the paper that kind of stimulated some of this additional work. And so they actually had in their paper the DFT determined exchange constants, which, in absolute units and everything. And this is the comparison. So it's not so bad in a sense, but there is a difference, which is there tends to be very clear evidence for a alternation in the sign of the exchange interaction that comes out in the experimental data, and less so in the DFT result. And we think that that's a distinction. But maybe the most important distinction is that there's a transverse interaction as well that we determine from the little rippling of the crystal field excitations, and those are really key to stabilize these canted spin structures that I was talking about. Those are not part of the DFT calculation yet, but of course this is like an experimental challenge to say, is it possible to calculate those kinds of things theoretically? Yeah. So then, let's see, how am I doing for time? That's an hour. Half an hour. Okay. Yeah. So this is. So I'm going to say a little bit more about these results. This is one of our good colleagues who's adjunct at the University, Predrag Nikolic, and he has developed a really beautiful analysis of this kind of Weyl-mediated exchange interactions, but where he uses a very, the simplest version that you could have of the Weyl band structure. So just a K.P type analysis of the electronic band structure. And what he finds is that in that case, the Giselle-Sitzke-Maria interaction takes this form where it's always oriented, the vector is always oriented along the bond that separates the two spins. So that is what comes out from that electronic band structure. But actually what we find experimentally is that it's the perpendicular to bond direction which is strong and important for these for the magnetic structure that we observe. So this was sort of a theory stimulating being able to extract these things. But now we see experimentally that it doesn't have the simplified form. And Dirac understands why that is. That's because in this, because the crystal structure doesn't really exist at all apart from just the two Weyl points. And so the lowering of symmetry that takes place in the crystal structure is not sort of it's not taken into account in this theory. And so he has worked and I think has developed a more advanced version of that. So this is kind of the interplay between the theory and experiment that you would expect. And Chris took another step, which was that he tried to really pin down the Sharavinsky-Maria interactions as well. And this was done by measuring this little canted component of the spin structure that I mentioned, the fact that the spins are kind of rocking back and forth. It turns out that they're not just rocking back and forth in a direction perpendicular to the wave vector, but they actually have this particular structure. This is an experimental result taken from a magnetic neutron diffraction. All of these angles and so on are now have been determined by Chris experimentally. And then what he's done is that he asked what kind of DM interactions are needed to stabilize this particular kind of canted structure. And it's quite involved, and you have to take a look at the paper to really assimilate it. But I just wanted to point out that this colored ring that indicates it reads off the phase angle that comes into to specifying the angle that the DM vector makes with the crystal lattice. So because this angle points to this kind of blue-greenish region, then that is the orientation of the DM vector that is inferred from this observed experimental structure. So this was how the DM vector and its orientation was established from the experiment. Okay, so then you could ask, well, how good is this very complicated? You could say complicated theory. It's in a sense it is. I think theorists would say this is a fairly simple theory, but it is complicated in the sense of the crystal structure is complex, and there are many different types of neoneighbors that have to be taken into account. How good is this theory to actually account for the experimental data? And it actually works really remarkably well. This is the specific heat, for example. That's the Schottky anomaly, which is well accounted for. These peaks are kind of critical phenomena that we shouldn't expect to account for, and so that they don't. This is a magnetization curve. All of the critical fields are accounted for. This is the temperature dependence of the moment, which is well accounted for, as well as the susceptibility as a function of temperature. So all of these things are really work pretty well, and we're then also able to really understand how the phase diagram for this kind of structure would change as you change the exchange constant. So the neodymium aluminosilicon lives sort of at this particular point in the phase diagram, but we can now sort of expand the phase diagram and think of what would happen when we put other rare sites into cerium, for example, and then we can understand why this 2/3 to 1/3 wave vectors is quite dominant. It occupies quite a big part of phase space, and so you gain an understanding of the broader nature of the structure. So just to conclude, we've been interested in what is special about the interactions, RKKY type interactions mediated by Weyl electrons. They're very anisotropic, and they have they induce a DM interaction that in turn induces this a non-collinear modulated spin structure. And we've been able to actually extract all of the interactions, and we are hoping for a continued engagement with theorists to understand really the nature of the interactions mediated by topological electronic band structures. So I wonder if you have any questions on that story so far. Yes?
So I was wondering, I had heard that DFT calculation is not very accurate when there are 4f electrons. Do you agree, considering that your result was compared with the DFT? Do you agree with that statement?
Yeah, it's true. I mean, in this case, the mitigating factor is that the F electrons are very far from the chemical potential. So then it's I think, fairly fairly good to treat them as fully localized, and that tends to be what is being done here. But it certainly is an approximation. That's probably why the comparison, in terms of the magnitude of the, somewhere here I had this kind of thing. It's not that great, but some of the features can be seen, but yeah, that it certainly is very complicated. It gets much harder when you come closer to chemical potential, for sure. Yeah. Yes?
Very nice talk. I have kind of a trouble understanding. So it seems like you have Weyl points near the pervious surface, and then obviously they're involved in the magnetism. Is there anything special that happens because they're Weyl points as opposed to some very heavily nested other kind of pervious surface?
That's a very good question. I think in a sense we can say no if one could say no, because this all is within the general kind of idea of what RKKY type interactions do. And you could even take it a step further. By symmetry analysis alone, you know that if there's a point of inversion between the two sites, then there cannot be a DM interaction. So you can kind of trim off some of the interactions that are not allowed by symmetry. And in this structure, because there isn't a point of inversion, you know that there are going to be all of these low symmetry interactions. And so at a sort of conceptual level, you could say, well, that is what RKKY interactions do, and I understand why we have these various terms. So that's, I think, is in a sense a fine way to say. But maybe we were kind of stimulated by the interest in the transport property that arises from Weyl points, and so in a sense you could say that just like the symmetry constraints and topology impose those aspects of the electronic band structure, then those become the kind of more detailed, the under the hood, what is actually causing the RKKY interactions to develop the DM term and to become anisotropic. So in that sense, there is a connection like that, but at the kind of broader 10,000 meter view, it really is the same kind of thing as an RKKY interaction. Okay, all right, so I'm going to take another step and try to look at the next kind of material, and that will be this one. So this is now going into transition metal site, and so now we're talking about systems where they're actually, the same orbitals, if you will, that are part of the electronic band structure near the chemical potential now are also being magnetic. So this is a 3D electrons, and so this brings a lot of additional complexity into it, and we have to somewhat lower our expectations in terms of what kind of accuracy we can achieve in the comparison between theory and experiment. On the other hand, these materials really have potential for applications and have some really, really interesting phenomena associated with them. These are my collaborators in this work, and I should, all of them have been very interesting for us to work with. I just mentioned Satoru Nakatsuji, who's both at University of Tokyo and Johns Hopkins, and has been a very long-term collaborator in this stuff. And he actually, together with a student, discovered the anomalous transport properties of this manganese-3 tin in 2011, and then really got us kind of involved in thinking about the magnetism of these things. Guy Marcus was a grad student who did some fantastic experiments both in Japan and in the States, and we've actually been working on some of his results since he graduated, but he was also involved in a lot of the analysis. And Yoshik Chen and Jonathan Godet was a student and a postdoc, respectively, working on this stuff. And I should say, for contractual reasons, since I'm at Johns Hopkins University, I have to mention that the Hall effect was discovered at Johns Hopkins University shortly after the foundation of the department, actually by Edwin Hall, who was a graduate student with Henry Rowland. And it's very interesting to read what he said about this. he said that he found this idea that was expressed in writings by Maxwell, that the Lorentz forces acting on electronic wires, that those really should be thought of as mechanical forces acting on the wire itself as opposed to on the carrier itself. And he found that kind of very weird. And he mentioned that to, he said that he had mentioned that, finding these two authorities, I brought the question to Professor Roland, and he told me that he also found it a little bit weird, and he would certainly encourage the experiments, but being very busy with other matters, he had no immediate intention of investigating this any further, which is really kind of amazing, because now we know how kind of fundamental this is, and if you have a hunch that something is not quite right in the inner workings of those kinds of things. But he was apparently too busy, but he had really a good hand in making it work experimentally, it turns out. He knew that he had to go to a very thin layer to be able to see this, and they were quite lucky, actually, picking materials that had effects that they could understand and discover then the regular Hall effect, if you will. Now this material, that was Satoru Nakatsu who discovered it, but what's interesting about that is that it has an anomalous Hall effect. So even in the absence of an applied field, if you train the sample, you have to initially apply a field, then you can withdraw the field, and then you'll actually see a Hall effect, and you can switch the sign of it as well. And so that's it's a very strong Hall effect, as strong as really an ion. So this is really a new kind of addition to it. And so this is the effect. So here you see the Hall resistivity as a function of field, and you have this little kind of hysteresis loop. And so you can actually withdraw the field entirely and still have a Hall signal, which is either positive or negative. I'll not mention that. And of course, this brings many different puzzle applications, both in terms of the Hall effect, the Nernst effect. We also have an anomalous Nernst effect. They're very interesting magneto-optical effects. And there's a spin-Hall effect. And all of these things actually have really, real prospects for applications because it's at room temperature, which is just astounding to us. We were always, for decades and decades, we were doing things at 0.3 Kelvin and saying, well, just wait, maybe we'll be able to raise it to 300. But this one is really, functioning right at room temperature. So that's really interesting to work on this kind of material. Now, the structure is very interesting and, of course, important for all of the properties. And it turns out that it's a stack of Kagame lattices. So this is one layer, and this is manganese on the colored sides here. And then we've got tin, and this spin structure was something that was, pretty much drawn by Satoru, and there were some early experiments, but it was not really quite clear what the spin structure was. But we later, and others as well, have really been able to determine that this is the non-collinear spin structure that developed. Now, the Kagame lattice we've been interested in for years, for many years, because of its frustrated magnetism. But that's when it exists as a two-dimensional structure. In this case, it's actually a layered structure, and there are very strong interactions between the layers. This is a metallic system, and so it really has, I would say, nothing to do with the spin liquid physics and stuff that people have wanted to see in the Kagame lattice. But it does have, obviously, to do with the triangular nature of the structure, as well as the kind of low coordination number. We could say that they play a role. But we were interested in trying to understand the magnetic interactions between the sites and understanding whether, was it two-dimensional or three-dimensional? And for that, we employ our inelastic scattering techniques. In this case, the energy range is quite different. We're up to hundreds of milli-electron volts. Yesterday, we were working down at micro-electron volts. So we changed the instrument, then we're up to this range. And basically, in this plot, for example, these are two different directions in momentum space. One is in the plane, the other is out of the plane, and you have pretty much the same kind of steepness of these curves, and that just directly shows that we have quite strong, the spin wave velocity is quite similar in the two directions, so there are quite strong interactions out of the plane. And working with our colleague Oleg Chernyshov and his students, they developed kind of a phenomenological description of spin wave excitations in these kinds of triangular lattice structures that is very interesting in its own right, and they've actually continued in that kind of research. For us, it was very helpful to be able to look at just low energy scattering, because at higher energies, it turns out that there's a lot of damping you can see it here. You know, we really just have the low energy part of the excitation, but at high energies, everything is damped because of the electron hole pair excitations, because it is a metal with quite high electron density. So we cannot do kind of a full fitting of these kinds of data, but we can, just by extracting the gap and the velocities, then we can get some information using the phenomenological theory of Chernyshov et al. And then we're able to see that it's actually this J2 interaction, which is interlayer interaction. Sorry, this is the in-plane Kagami interaction, antiferromagnetic, but then there's a ferromagnetic interplane interaction, which is equally strong, actually. These then give rise, along with the DM interaction, which also plays an important role, they give rise to this, to the particular spin structure that is observed, which is an anti-chiral spin structure. Now, to really determine that spin structure is actually quite not so straightforward. And there are a couple of reasons for that. One is that it's a so-called Q equals to 0 spin structure. And that means that the chemical unit cell equals the magnetic unit cell, which means that all the Bragg peaks, the magnetic Bragg peaks, just fall on top of nuclear Bragg peaks. So I'm just going to change the intensity of some nuclear Bragg peaks a bit as a result of the magnetic structure. That is actually becomes a bit of a challenge. But in addition, it's a non-collinear spin structure. And so there's many aspects of it that really cannot be determined, let's say, by conventional unpolarized neutron diffraction. And so we have actually employed polarized neutron diffraction, and I wanted to take the opportunity to say a few words about that. However, the time has expired.
Oh, no, we're good.
We still, okay. Yeah, so let me just say a few words about polarized neutron diffraction, which is really kind of a cool technique. So this is what we've been talking about so far, just having an incident wave vector, a scattered wave vector, transferring momentum to the sample, but we didn't really keep track of the electron spin as much. We were always summing over incident spin state and scattered spin state. And you could say, why did we do that? That's because we wanted to maximize flux, so we didn't want to get into the trouble of trying to determine the spin state of the incident neutron, nor casting away the spin state of the some of the scattered neutrons. So that's kind of the high intensity experiment, and it works pretty good. But it's even more specific if you can keep track of the spin, and so that's what we're going to do next. We'll keep track of this spin and this spin, and we'll know what angular momentum was transferred by the spin flip process to the sample. And this can be done both for inelastic scattering and for elastic scattering. And the cross section gets more complicated, but that complexity allows us to extract more information from the process. There's a lot of kind of technical aspects of it. We have to polarize the neutrons, which we can do in a number of different ways. We can use helium-3 as a polarized gas. So you can actually polarize helium-3, and then you pass neutrons through, and half of them are absorbed and the other half come through as a polarized neutron beam. That's one way of doing it. That's pretty nice, but you lose half of your neutrons and a bit more. So that's kind of unfortunate. Then there's polarized diffraction, which is where you use a ferromagnetic material and you use the nuclear magnetic interference effect to eliminate one spin state, and the other spin state will be diffracted. So that also loses you half of the neutrons, because the half that didn't diffract just passed through the monochromator. But we use that sometimes. You can also use a supermirror polarizer, which is a magnetic thin film that has a different index of refraction for the two different spin states. And so one of the spin states will be guided through the system, and the other spin state will be lost again. Again, you lose half of it. You can also, we've been thinking about using a system where you just split the two beams apart and use both of them. We haven't been able to do this yet, but this is kind of an idea to not have to lose the neutrons. We've used this in the past, and many people have in the past used this. This was a case of nickel vanadate, which has this kind of counterclockwise and clockwise domains of a chiral form of magnetism that is combined with electric polarization, and the different handednesses are associated with different directions of the electric polarization. And so in that case, we were able to, by applying an electric field, get get high intensity in the one or the other spin channel. And so you could really, separate out how much of your sample was in this state as opposed to in this state. And so that was kind of a unique application of polarized neutrons. There's another related technique that's called neutron polarimetry, which I won't be able to fully describe, but it involves measuring for each Bragg peak, actually determining the transfer matrix that transfers the incident neutron spin state to the final neutron spin state. So neutron comes in, it diffracts, but that actually rotates the spin state to some other orientation, and then it leaves the sample. And so in this case, the experiment is done inside a superconducting shield. So this is really in a zero field regime. And then the neutron is extracted from that, and you measure the full kind of transfer matrix. So that gives you a whole matrix, like a rotation matrix for each Bragg peak. And that's a much more detailed kind of information. It's called neutron polarimetry. Very cool technique. And it's needed really for complex structures. In this case, manganese tin, we could use it to separate out the magnetic and the nuclear part of the diffraction cross-section. So here's experiment on the 100 diffraction peak in manganese tin. And I am showing you in very different colors. That corresponds to various different channels of polarization. So I have part of the experiment, I'm having a horizontal guide field, which makes sure that the incident neutron is polarized along the wave vector transfer. That's this row here. And part of the experiment, I have a vertical guide field, which makes sure that the incident neutron spin is polarized perpendicular to the scattering plane. I have to study this a bit more, so I'm sure it's the case for you as well, but we kind of, keep track of the incident neutron, and we choose specific orientations that allow us to bring out specific parts of the cross-section. And so there are now, I can either have a process that flips the neutron spin, or I can have a process that doesn't flip the neutron spin, and I keep track of the intensity in each of those channels. I measure them separately. I have to spend time measuring the one, then the other. And for example, the non-spin flip channel with the neutron polarized along the wave vector transfer, that has only nuclear intensity in it. That's the blue one, so that is the nuclear intensity in this peak. It's as much as this blue point here. On the other hand, when I take spin flip, again with neutrons polarized along wave vector transfer, then I get all of the spin polarization, which is normal to wave vector transfer, and that's the orange peak. So this has broken down the nuclear contribution and the magnetic contribution, and that's really, a really wonderful thing, because I can know for sure how much is magnetic, how much is nuclear. If I do unpolarized, I'm just going to see the sum of those two, and I can see the sum of those two. Actually, sorry, I can see the sum when I go to this channel here. So it's a non-spin flip channel with vertical field, and then you can see that summing these two to each other, I'll get up to this number. That's fine. But there's one more point I should mention, which is this channel is very, very helpful, even though there's no intensity at all to be seen. So that channel is only sensitive to the magnetization, which is along the c-axis, so normal to the Kagame planes. But we see absolutely nothing there. So that shows us that this really is a planar structure. The spins are really in the plane. So this is really just categorical information that comes out from this kind of experience. That's why we like it. So then, let's see. Then we now go to the low temperature state. So this material again has a high temperature. Sorry, this material is kind of the other way around. Has a commensurate structure at high temperatures, then an incommensurate structure at lower temperatures. And maybe I should say, by showing this, I should show what the commensurate and incommensurate structure look like. So this is the commensurate structure. So similar to what was shown in the first slide. And it is an anti-chiral structure. So and the reason I call it anti-chiral is if I take a walk around the triangle, then if I go sort of in the clockwise direction, you'll find that the spins are actually rotating in the counterclockwise direction. So this spin to go from this spin So this spin, I rotated in the counterclockwise direction. So that's the nature of the structure. That's absolutely crucial. Had it been clockwise rotation, then I wouldn't have had all of this anomalous Hall effect at all. So it's all tied to the handedness of the rotation. Because of that, the symmetry is really that of a ferromagnet, and because of that, the Dirac point is split into Weyl points when this magnetic structure develops, and because of that, I have anomalous Hall effect. So it all kind of hangs together like that. So this is what the experimental data, which was both polarized and unpolarized neutrons to figure this out. But then when we come into when we cool the system down, it all hell kind of breaks loose, and we get into this really, really complicated modulated structure. So what's happening is that this antichiral state is actually rotating from plane to plane. So as I come out along the z-axis, then all of the spins are rotated by some amount. They actually rotate together, and then this is why I'm looking at it as if I'm looking from above. But in addition, there's actually a component of the spin which is coming out of the plane along the z-axis. And so this we saw very, very clearly because suddenly there was that component that you didn't see when the red trace now suddenly appears. And so we know that the spins are not only kind of rotating in the plane, but they actually also kind of oscillating out of the plane. And we have a pretty good determination of that structure. It's actually easier to determine this structure in a sense than this structure. And that's because in this case, the Bragg peaks move away from the nuclear Bragg peaks, and then you can suddenly kind of do it. So this was just a total surprise actually, which was we used polarized neutrons to resolve the incommensurate peaks that had been observed. And so here I'm showing you data at 2 different temperatures. It's all in the incommensurate state, 250, then 100 Kelvin. And this had previously been just one peak when we used polarized neutrons. But we hadn't really noticed there were 2 peaks. There was a little bit of something, but then when we used polarized neutrons, they're totally split out from each other. And then furthermore, you'll see that the red one is higher Q than the low one is green. And then they switched at lower temperatures. So that these peaks are actually moving about and kind of cross each other. And it turns out that one of the peaks has to do with an in-plane rotation. That's the kind of the rotating of the spins within the plane. The other has to do with the out-of-plane spin excursions out of the plane, and they have different wave vectors. So it's a really enormously complex structure, and we eventually resorted to using X-ray, synchrotron X-ray diffraction, both magnetic and both resonant, enhanced, and regular X-ray diffraction to actually pull out these different components because the resolution is so much better than we can achieve. And there you could actually see this. We had sort of 2 components of wave vector that are converging on each other. Then for a brief period of temperatures, they kind of stick together at the same value, and then they separate out and become separate traces. So it's a really quite complicated incommensurate structure that develops. And when that structure develops, we completely lose the Hall response. So this is in the commensurate phase, in the antichiral state. But once all of this rotation takes place, then we just totally lose it. And that is as you should expect, because I no longer have, it corresponds to having a ferromagnet with all possible different rotations or orientations at the moment. And so there's no longer a ferro character to the structure at all, and we lose that. So it's important to understand, what eventually eliminates the effect that we are interested in. Also in this case, we're able to relate the incommensurate wave vector to nesting conditions on the Fermi surface. It's now a fairly complicated Fermi surface, but the large areas are separated from each other by wave vectors very close to those that we observe in the X-ray diffraction experiment. Well, so I think with that, I should probably come to a close. And I think I have a few words I was going to say about this little friend, which is, we've looked at the magnetic orders using polarized neutrons, and we've analyzed the spin wave excitations. Those are heavily damped at high energies, which is what you expect when you're dealing with magnetism that's carried by the same bands that are also conducting charge. And so there's always a lot of excitations possible that lead to damping. We've analyzed this complicated incremental structure that actually eliminates the anomalous Hall response. And then just to kind of summarize my stories here, yesterday we were talking about insulating transition and rare earth systems as really laboratories to study quantum antibody physics. Using similar techniques, we can try to understand the interplay between magnetism and topological metallic systems. And I didn't get to talk about the superconductor, but in that case we were using actually muon spin relaxation to probe this kind of mixed type 1, type 2 system. And then just to my kind of takeaway messages, if you will, I know we have both experimental people working experimentally and theoretically, and I would just generally say, consider using neutrons and muons to enrich your studies of quantum materials. You tend to get very decisive kind of specific microscopic information. The experiments are maybe more complicated in a sense, and they're maybe less helpful in terms of exploring the phase space of materials, but when you have something that looks interesting and you have a question that's very hard to answer, sometimes you can really get it by these techniques, so I encourage you to take a look. You'll find the facilities very willing to interact with you when you've got interesting results, interesting materials. And for the theorists, I think it's very important to maintain your skepticism about the conclusions that people draw from experiments, and it becomes important to actually be quite knowledgeable about what they're really doing and what the raw information is. When you read the conclusion of the paper, maybe this is what it is, but actually very often there's some modifications that are needed. And it's actually very useful to engage in that sense and in general to kind of help elevate the quality of the engagement between theory and experiment, which is really key to what we're doing in physics. So thank you very much for your attention.
Do we have time for one quick question? Yeah.
Sorry. So I guess I don't. Why do you get like a ferromagnetic symmetry to rotate one way but not the other way?
So let me just go back to this picture here. Right. Yeah. This picture. Okay. So this structure has actually the symmetry properties of a ferromagnet. So this is not entirely, so just to argue why that is the case, then let me see. Okay, so the point is that I have three vectors here, which are adding up to 0. They form actually a triangle, and they add up to 0. However, we are in a crystal structure, and these spins are actually oriented along different directions, quote-unquote different directions. These spins point between manganese sites. This spin points between two manganese sites. This one points between two manganese sites. But this spin is the same spin as this one, for example. It points between two sites which have a tin atom on them. And you might say, well, that should be fine. It's still a manganese spin. However, once you take into account all of the different kinds of chemistry and interactions that could be present, then this spin cannot have exactly the same length as these other spins. It will have to be modified as a result of it being really in a different orientation. And therefore, I cannot really close this triangle anymore, and I end up having a finite magnetization associated with this structure. And it will just have a small magnetic moment. That turns out to be 7 millieV per manganese, which is just kind of a remnant moment that cannot be eliminated as a result of these things. And so that little remnant moment, you might say, well, that has no, like if I calculate the B field induced by that, that will definitely not be enough to cause significant like Hall response. However, because of the symmetry that it carries, the fact that now time reversal symmetry is actually causing the flipping of this entire structure, then that ensures that there will be the possibility of a split electronic band structure, and then you get all of the Weyl physics and everything sort of comes out of it. So that's the story basically. And so once we begin to rotate this from layer to layer, then the orientation of this kind of fictitious magnetic moment, which is so important for the transport properties, that orientation is now kind of scrambled, and I really lose the macroscopic effect.
All right, let's thank Professor Broholm once more.